The night sky spreads above us like a canvas without edges, stars scattered across the dark in patterns we've traced for millennia. We look up and see depth, distance, an expanse that seems to go on forever. But what if it doesn't? What if somewhere out there, far beyond anything we can see with our eyes or our instruments, the universe simply stops? Before we go further, if you're watching on a smaller screen, consider switching to full screen to truly appreciate what we're exploring together. And if this kind of deep investigation into the cosmos resonates with you, subscribe so we can continue mapping the furthest boundaries of existence. Now, let's turn our attention to one of the most profound questions in all of science: whether the universe we inhabit has an edge, and whether we're closer than ever to finding it. The question itself feels almost forbidden, as though asking it violates some unspoken rule about the nature of reality. We've been taught, most of us, that the universe is infinite, or at least so vast that the difference between infinite and incomprehensibly large becomes meaningless. We've grown comfortable with the idea that no matter how far we travel in imagination or instrumentation, there will always be more universe ahead of us, more galaxies, more space, more time. But comfort and truth are not the same thing, and the universe has never been obligated to conform to our intuitions or our preferences. To understand why scientists are now seriously considering the possibility of a cosmic edge, we need to step back and examine what we actually know about the structure and extent of the universe, as opposed to what we assume or hope. The story begins not with boundaries, but with expansion, with the realization that came nearly a century ago that the universe is not static. Edwin Hubble, working with the 100-inch telescope on Mount Wilson, measured the light from distant galaxies and found something unexpected. The light was shifted toward the red end of the spectrum, stretched out as though the galaxies themselves were moving away from us. And the farther away a galaxy was, the faster it seemed to be receding. This was not a simple case of things flying apart after some ancient explosion, though that's often how it's described in popular accounts. The galaxies aren't moving through space in the conventional sense. Instead, space itself is expanding, carrying the galaxies along with it, like raisins in a rising loaf of bread. The dough expands, and the raisins move apart, not because they're traveling through the dough, but because the dough between them is growing. This expansion is happening everywhere, at all points in space, all at once. It's not expanding into anything, because there is no outside for it to expand into. The universe is all there is, and it's getting bigger. This picture of an expanding universe immediately raises questions about beginnings and endings, about where the expansion came from and where it might be going. If we run the expansion backward in time, we find that the universe was once smaller, denser, hotter. Keep going back, and everything we see around us, all the matter and energy in the observable universe, was once compressed into a region smaller than a single atom. This moment of extreme density and temperature is what we call the Big Bang, though the name is misleading. It wasn't an explosion in space. It was an explosion of space, a sudden eruption of space-time itself from a state we still don't fully understand. But here's where things get interesting, and where the question of an edge begins to take shape. When we talk about the Big Bang, we're talking about the beginning of the observable universe, the region of space from which light has had time to reach us since the beginning. We can see back to a time roughly 13.8 billion years ago, to an era when the universe was so hot that atoms couldn't form, when matter and radiation were mixed together in a dense, opaque plasma. As the universe expanded and cooled, atoms finally formed, and light could travel freely for the first time. That light has been traveling toward us ever since, stretched and cooled by the expansion of space, and we detect it today as the cosmic microwave background radiation, a faint glow that fills the entire sky. The cosmic microwave background represents a kind of horizon, the most distant thing we can possibly see with light. Beyond that horizon, there is more universe, regions of space that exist, but from which light has not yet had time to reach us. The observable universe is therefore not the entire universe. It's just the part we can see, a sphere centered on us with a radius defined by the speed of light and the age of the universe. The question is whether the universe beyond our observable horizon goes on forever, or whether it eventually comes to an end. For decades, the standard assumption was that the universe is either infinite or so close to infinite that the distinction doesn't matter. This assumption was based partly on theoretical considerations and partly on measurements of the geometry of space. Einstein's general theory of relativity tells us that space can be curved by the presence of matter and energy, and that the overall shape of the universe depends on its total density. If the density is exactly equal to a certain critical value, space is flat, extending infinitely in all directions, like an endless sheet of paper. If the density is higher than the critical value, space curves back on itself like the surface of a sphere, creating a finite universe with no edges. If the density is lower, space curves the other way, creating a saddle-shaped geometry that is also infinite. Measurements of the cosmic microwave background, particularly from satellites like WMAP and Planck, have shown that the geometry of space is very close to flat, so close that we can't rule out perfect flatness within the limits of our instruments. A flat universe is typically assumed to be infinite, stretching on forever in all directions. But here's the crucial point. Flat doesn't necessarily mean infinite. A flat space can be finite if it has a particular topology, a particular way of connecting back on itself. Imagine a video game where you walk off the right edge of the screen and appear on the left edge, or walk off the top and appear at the bottom. The screen is flat, but the space it represents is finite, wrapped around on itself in a way that has no edges or boundaries. The universe could be like that, flat but finite. And if it is, then there's a sense in which it has an edge, not a physical boundary you could run into, but a limit to how much space there is. Recent work by cosmologists has started to take the possibility of a finite universe more seriously, driven in part by subtle anomalies in the cosmic microwave background, and in part by theoretical considerations about the nature of inflation, the rapid expansion that is thought to have occurred in the first fraction of a second after the Big Bang. Inflation was proposed to explain several puzzles about the early universe, including why space is so flat and why the cosmic microwave background looks almost the same in all directions. The idea is that the universe underwent a brief period of exponential expansion, growing by an enormous factor in an incredibly short time. This expansion smoothed out any irregularities and stretched space so much that any initial curvature became negligible, leaving the universe flat, or very nearly so. But inflation raises its own questions, and one of them concerns the extent of the universe. If inflation happened, it didn't necessarily happen everywhere. It could have occurred in a finite region, a bubble within a larger structure, And what we call the universe might just be the inside of that bubble. Outside the bubble, space might be different, or there might be other bubbles, other regions where inflation occurred, but with different properties, different laws of physics. This is the idea behind the multiverse, a vast collection of separate regions, each potentially infinite in its own right, but collectively forming a structure that could have boundaries, transitions, edges of a sort. Even within our own bubble, though, the question of edges persists. The observable universe is definitely finite, limited by the speed of light and the age of the universe. But what about the universe beyond what we can see? Is it infinite, or does it have a limit? One way to approach this question is to look for patterns in the distribution of galaxies and other structures, patterns that might reveal the overall shape and extent of space. When astronomers map the positions of galaxies across large swaths of the sky, they find that galaxies are not distributed randomly. They're organized into a vast cosmic web with galaxies clustered along filaments and sheets, separated by enormous voids where very few galaxies exist. This structure formed over billions of years through the action of gravity, as regions that were slightly denser than average attracted more matter, growing into the clusters and superclusters we see today. The cosmic web extends as far as we can see, out to distances of billions of light years, and everywhere we look, the pattern is roughly the same. On very large scales, the universe looks homogeneous and isotropic, the same in all directions and at all locations, at least within the observable universe. But homogeneity and isotropy are statistical properties, averages over large volumes of space. On smaller scales, there are deviations, fluctuations, regions where the density is higher or lower than average. These fluctuations are the seeds from which all structure grew, and they're imprinted in the cosmic microwave background as tiny temperature variations, hot spots and cold spots that differ by only a few parts in 100,000. The pattern of these fluctuations tells us a great deal about the early universe, about the density of matter and energy, about the geometry of space, and potentially about the overall size and shape of the universe. One of the most intriguing aspects of the cosmic microwave background is that it contains information not just about the early universe, but also about the topology of space. If the universe is finite and has a particular shape, then light traveling through it might take multiple paths to reach us, wrapping around the universe and arriving from different directions. This would create a pattern of correlations in the cosmic microwave background, a kind of signature that could reveal the size and shape of space. Cosmologists have searched for these correlations, looking for repeated patterns or symmetries in the temperature fluctuations. And while some studies have claimed to find hints of such patterns, the results remain controversial and inconclusive. The universe, if it is finite, is large enough that any topological signatures are subtle and difficult to distinguish from random noise. Another approach to the question of cosmic boundaries involves looking at the large-scale structure of the universe, not just the distribution of galaxies, but also the distribution of matter and energy on the very largest scales. One of the tools for this is the study of baryonic acoustic oscillations, subtle ripples in the distribution of matter that were created by sound waves in the early universe. These oscillations provide a standard ruler, a known distance scale that can be used to measure the expansion history of the universe and to test models of its geometry and composition. So far, measurements of baryonic acoustic oscillations are consistent with a flat, homogeneous universe. but they also leave room for more exotic possibilities, including a finite universe with a complex topology. The question of whether the universe has an edge also intersects with the question of what lies beyond the cosmic horizon, the boundary of the observable universe. Light from regions beyond this horizon has not yet had time to reach us, so we can't observe them directly. But that doesn't mean they don't exist, and it doesn't mean we can't make inferences about them. One way to think about this is to consider the uniformity of the observable universe. Everywhere we look, the large-scale structure is similar. The distribution of galaxies follows the same patterns. The cosmic microwave background has the same average temperature. This suggests that the regions just beyond our horizon are probably similar to the regions we can see. If the universe changes dramatically at some distance, we might expect to see some signature of that change in the parts we can observe, some asymmetry or gradient that points toward a boundary. And here's where things start to get interesting, because there are hints, subtle and controversial, that the universe might not be as uniform as we thought. Some studies of the cosmic microwave background have found evidence for anomalies, features that don't quite fit the standard model of a homogeneous isotropic universe. One of these anomalies is the so-called axis of evil, an alignment of the largest scale temperature fluctuations in the cosmic microwave background. In a perfectly isotropic universe, there should be no preferred direction, no axis along which the fluctuations line up. But the data from WMAP and Planck suggest that such an axis exists pointing toward a particular direction in space. The statistical significance of this alignment is debated, and it could be a fluke, a consequence of how we analyze the data, or of foreground contamination from our own galaxy. But if it's real, it could be a sign that the universe is not isotropic, that there's some large-scale structure or boundary that breaks the symmetry. Another anomaly is the cold spot, a region of the cosmic microwave background that is significantly colder than average, covering an area of the sky much larger than typical fluctuations. The cold spot was first identified in the WMAP data and confirmed by Planck. Various explanations have been proposed, including the possibility that it's caused by a supervoid, an enormous region of space with lower than average density through which light from the cosmic microwave background passes and loses energy. But the cold spot is colder and larger than simulations predict for a supervoid, and some researchers have speculated that it could be evidence of something more exotic, perhaps a collision between our universe and another bubble in a multiverse, or a signature of the finite size of the universe. These anomalies are tantalizing, but they're also frustratingly ambiguous. The cosmic microwave background is a noisy dataset, full of foreground signals from dust and radiation in our own galaxy, and from the Sunyaev-Zeldovich effect, the distortion of the background light as it passes through hot gas in galaxy clusters. Separating the true primordial signal from these contaminants is a complex and uncertain process, and it's possible that the anomalies are artifacts of this separation rather than genuine features of the universe. But the fact that multiple independent analyses have found similar anomalies using different methods and different data sets suggests that there might be something real here, something that challenges the standard model of cosmology. Beyond the cosmic microwave background, there are other observations that hint at large-scale structure and possible boundaries. One of the most striking is the discovery of enormous cosmic voids, regions of space hundreds of millions of light years across, that contain very few galaxies. These voids are not empty. They still contain dark matter and dark energy, and the occasional galaxy, but they're significantly less dense than the average. The existence of such voids was predicted by simulations of cosmic structure formation, but the largest voids observed are at the upper end of what the simulations predict, and some are even larger than the models suggest should exist. The largest of these structures is the Hercules Corona Borealis Great Wall, a filament of galaxy clusters stretching across more than 10 billion light years. The existence of such a structure challenges the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. If structures this large exist, it suggests that the universe might have more complexity, more hierarchy than we thought, and it raises the question of what happens at even larger scales. Do structures continue to grow indefinitely, or is there a scale at which the universe becomes smooth, a scale that might represent a fundamental limit? Another line of evidence comes from studies of the large-scale velocity field, the motion of galaxies and galaxy clusters relative to the cosmic microwave background. According to the Standard Model, these motions should be caused by gravitational attraction toward overdense regions and repulsion from underdense regions, and the pattern of motions should reflect the distribution of matter. But some studies have found evidence for a large-scale bulk flow, a coherent motion of galaxy clusters in a particular direction, extending out to distances of hundreds of millions of light years. This bulk flow is larger and more coherent than the Standard Model predicts, and its existence suggests that there might be some large-scale structure or inhomogeneity beyond the observable universe, pulling on the matter we can see. This brings us to one of the most profound implications of the possibility that the universe has an edge. The idea that what we observe might be influenced by what we can't observe. If the universe is finite, or if there are large-scale structures or gradients beyond our cosmic horizon, then the matter and energy in those regions could exert a gravitational influence on the observable universe, creating patterns and asymmetries that we can detect. This is sometimes called the cosmological horizon problem, and it highlights the fundamental limitation of observational cosmology. We can only see so far, and everything beyond that limit is hidden from us, yet it might still affect what we see. The question of cosmic boundaries also connects to the nature of dark energy, the mysterious force that is causing the expansion of the universe to accelerate. Dark energy was discovered in the late 1990s when astronomers studying distant supernovae found that they were dimmer than expected, implying that the universe's expansion was speeding up rather than slowing down. The power spectrum encodes information about the geometry, composition, and history of the universe, and any deviation from the expected pattern could be a sign of new physics or of a finite universe. The data from Planck and other experiments have measured the power spectrum with exquisite precision, and while the overall pattern matches the predictions of the Standard Model, there are subtle deviations at the largest scales that could be hints of something more. One of these deviations is a deficit of power at the largest scales, a lack of temperature fluctuations on scales comparable to the size of the observable universe. This could be explained by a finite universe, where the largest possible fluctuations are limited by the size of space. If the universe is finite and has a particular topology, then the power spectrum should be suppressed at scales larger than the fundamental scale of the topology. Some analyses of the Planck data have found evidence for such a suppression, suggesting that the universe might be finite with a size comparable to or slightly larger than the observable universe. But other analyses have found no such evidence, and the question remains open. Another approach to detecting cosmic boundaries is to look for patterns in the distribution of galaxies and galaxy clusters. If the universe has a large scale structure or gradient, it should show up as a preferred direction or an asymmetry in the number counts of galaxies, in their clustering properties, or in their redshifts. Several studies have claimed to find such asymmetries, including claims of a dipole, a pattern where there are more galaxies in one direction than in the opposite direction, that is larger than the standard model predicts. These claims are controversial and have been challenged on methodological grounds, but they add to the growing sense that the universe might be more complex and less uniform than the standard model assumes. The question of cosmic boundaries also intersects with the physics of black holes and the nature of spacetime itself. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They have a boundary called the event horizon, beyond which events cannot influence the outside universe. In a sense, a black hole is a kind of edge, a place where space-time ends or at least becomes inaccessible. Some theorists have speculated that the universe as a whole might have a similar structure, with regions that are causally disconnected from us, separated by horizons that we can never cross or see beyond. This idea is formalized in the concept of the cosmological event horizon, the boundary beyond which events can never influence us, because the expansion of space is carrying them away faster than light can travel. In a universe dominated by dark energy, the cosmological event horizon is a real thing, a sphere surrounding us beyond which we can never receive information. Galaxies that are currently beyond this horizon are lost to us forever, and as the universe continues to expand, more and more galaxies will cross the horizon and disappear from view. In this sense, the observable universe is shrinking even as space itself expands, and the edge of what we can see is moving inward, bringing us closer to a kind of boundary. But there's a deeper question here, one that touches on the very nature of reality. If there are regions of space that we can never observe, regions beyond our cosmic horizon or beyond the boundaries of our bubble in a multiverse, do those regions exist in any meaningful sense? This is not just a philosophical question. It has implications for how we do science and what we consider to be evidence. In traditional science, we test theories by making predictions and comparing them to observations. But if a theory makes predictions about regions of space that are fundamentally unobservable, how can we test it? How can we distinguish between a theory that's correct and one that's wrong if both make the same predictions for the observable universe? This is sometimes called the problem of the multiverse, and it's a source of ongoing debate among physicists and philosophers. Some argue that theories that postulate unobservable regions are not scientific because they can't be tested. Others argue that such theories can still be scientific if they make predictions about the observable universe that can be tested, even if those predictions arise from a larger structure that includes unobservable parts. The question of cosmic boundaries is intimately tied to this debate, because if the universe has an edge or a boundary, it might be located in a region that we can never observe, and we might only be able to infer its existence from indirect evidence. One form of indirect evidence could come from the study of gravitational waves, ripples in spacetime caused by the acceleration of massive objects. Gravitational waves were first detected in 2015 by the LIGO experiment, confirming a prediction of Einstein's general relativity and opening a new window on the universe. Since then, dozens of gravitational wave events have been detected, mostly from merging black holes and neutron stars. But gravitational waves also carry information about the large scale structure and geometry of the universe. And future gravitational wave observatories could potentially detect patterns or asymmetries that reveal the presence of cosmic boundaries or large scale inhomogeneities. Another potential source of evidence is the study of ultra high energy cosmic rays, particles that strike the Earth's atmosphere with energies far higher than anything we can produce in particle accelerators. The origin of these cosmic rays is a mystery. They seem to come from beyond our galaxy, but their trajectories are bent by magnetic fields, making it difficult to trace them back to their sources. Some researchers have suggested that the distribution of ultra high energy cosmic rays might reveal large scale structure or asymmetries in the universe, including the possible presence of boundaries or gradients. If there's a region of space where the density of sources is different, or where the magnetic fields are structured differently, it might show up as an asymmetry in the arrival directions of cosmic rays. The search for cosmic boundaries also involves thinking carefully about what we mean by an edge. In everyday experience, an edge is a place where something ends, where you can go from inside to outside. But in cosmology, the concept is more subtle. Space doesn't have to end in the sense of having a physical barrier or a boundary you could run into. It could be finite and yet have no edges, like the surface of a sphere. Or it could be infinite in some directions and finite in others. Or it could have a more complex topology with wormholes or other connections that link distant regions. The question is not just whether the universe has an edge, but what kind of edge it might have and what that would mean for the structure of space and time. One of the most radical possibilities is that space itself is emergent, that it's not a fundamental feature of reality, but something that arises from a deeper level of description. In this view, space and time are like temperature or pressure, macroscopic properties that emerge from the collective behavior of microscopic constituents. The constituents might be something like quantum bits of information or quantum entanglement or some other structure that we don't yet understand. If space is emergent, then the question of whether it has boundaries depends on the properties of the underlying structure. The universe might be finite at the fundamental level, with a limited number of degrees of freedom, even if the emergent space appears to be infinite or very large. This idea is motivated in part by developments in quantum gravity, the attempt to reconcile quantum mechanics with general relativity. Quantum mechanics describes the behavior of particles and fields on very small scales, while general relativity describes the behavior of space and time on large scales. The two theories are incompatible in their current forms, and physicists have been searching for a unified theory that combines them. One of the leading candidates is string theory, which proposes that the fundamental constituents of reality are not particles, but tiny vibrating strings. In string theory, space can have extra dimensions beyond the three we experience, and these extra dimensions might be finite, curled up into tiny shapes that we can't perceive directly. Another approach to quantum gravity is loop quantum gravity, which proposes that space itself is quantized, made up of discrete units like atoms of space. In this picture, space is not continuous but has a granular structure at the smallest scales, and this granularity could have implications for the large-scale structure and extent of the universe. If space is quantized, then the universe might be finite, with a total volume determined by the number of discrete units. Alternatively, the universe could be infinite, but have a complex structure at the smallest scales that affects how it evolves and expands. These ideas are highly speculative and far from proven, but they illustrate the range of possibilities that cosmologists and theoretical physicists are exploring. The question of whether the universe has an edge is not just an empirical question that can be answered by observation alone. It's also a theoretical question that depends on our understanding of the fundamental nature of space, time, and matter. And it's a question that pushes us to the limits of our current knowledge, forcing us to confront the boundaries, not just of the universe, but of what we can know and understand. One of the most intriguing aspects of the search for cosmic boundaries is the role of symmetry. Symmetry is a powerful concept in physics, a principle that underlies many of the fundamental laws of nature. The laws of physics are symmetric under translations in space and time, meaning that they work the same way here as they do there, now as they do later. They're also symmetric under rotations and boosts, transformations that change your orientation or velocity. These symmetries are encoded in the structure of spacetime and in the equations that govern the behavior of matter and energy. But symmetries can be broken, and when they are, interesting things happen. In the early universe, for example, the symmetry between different fundamental forces was broken as the universe cooled, leading to the distinct forces we observe today: electromagnetism, the weak nuclear force, and the strong nuclear force. The breaking of symmetry created structure, diversity, complexity. And it's possible that the universe as a whole has a broken symmetry, an asymmetry that reflects the presence of a boundary or a large-scale structure. If the universe is not isotropic, if there's a preferred direction or a gradient, it means that the symmetry of space has been broken, and that breaking could be a clue to the underlying structure of reality. One way to think about this is to consider the universe as a system with boundary conditions. In physics, boundary conditions are constraints that specify the behavior of a system at its edges or at infinity. For example, when you solve the equations for the motion of a vibrating string, you need to specify the boundary conditions at the ends of the string, whether they're fixed or free to move. The solutions depend on these boundary conditions, and different boundary conditions give different modes of vibration. Similarly, the structure and evolution of the universe depend on its boundary conditions, on what happens at the edges or at infinity. If the universe is infinite, the boundary conditions are specified by the behavior of fields and matter as you go to infinity. If the universe is finite, the boundary conditions are specified by the topology, by how space wraps around on itself, or by what happens at the actual edges if they exist. The cosmic microwave background provides a way to probe these boundary conditions, because the pattern of temperature fluctuations depends on the geometry and topology of space. If space is flat and infinite, the fluctuations should follow a particular statistical pattern with power at all scales. If space is finite, the pattern should be different, with a cutoff or suppression at scales larger than the size of the universe. By analyzing the cosmic microwave background in detail, we can constrain the possible boundary conditions and potentially detect evidence for a finite universe. But there's a complication, which is that the cosmic microwave background itself has a boundary, a last scattering surface that marks the moment when light decoupled from matter and began traveling freely through space. Before that moment, the universe was opaque, and we can't see directly what happened earlier. We can infer the conditions in the earlier universe from the pattern of fluctuations we see in the cosmic microwave background. But there's a limit to how much information we can extract. The last scattering surface acts as a kind of veil, hiding the earliest moments of the universe from direct observation. Beyond the last scattering surface, there are other horizons, other boundaries in time. The most fundamental is the Big Bang itself, the moment when the universe began. But even the Big Bang might not be the ultimate beginning. Some models of inflation suggest that the Big Bang was not the beginning of everything, but just the beginning of our particular bubble, our region of space. Before the Big Bang, there might have been a pre-existing state, a false vacuum or a quantum fluctuation from which our universe emerged. And if that's the case, then the question of boundaries becomes even more complex, because the universe might have a boundary in time as well as in space, or it might be part of a larger structure that has always existed in some form. These questions about boundaries in time connect to deep issues in the philosophy of time and causality. If the universe had a beginning, what came before? If it didn't have a beginning, how can an infinite amount of time have already passed? These are ancient questions debated by philosophers and theologians for centuries, and modern cosmology has brought them into the realm of empirical science. We can now make measurements, collect data, test models, and the answers we find will shape our understanding of reality in profound ways. One of the key insights from modern cosmology is that time is not absolute but relative, intimately connected with space in the structure of spacetime. In Einstein's relativity, time is a dimension like space, and the distinction between past, present, and future is not fundamental, but depends on your frame of reference. This means that questions about the beginning or end of time are not separate from questions about the structure and extent of space. If the universe has a boundary in space, it might also have a boundary in time, or the two might be connected in ways we don't yet understand. The concept of a cosmic edge also raises questions about what it would mean to approach such an edge. In science fiction, travelers often encounter boundaries at the edge of the universe, walls of energy or transitions to other dimensions. But in reality, the experience of approaching a boundary would depend on the nature of the boundary and the laws of physics. If the universe is finite but has no edges, like a sphere, then you could travel forever in a straight line and eventually return to where you started, never encountering a boundary. If the universe has a topological edge, a place where space wraps around on itself, you might pass through the edge without noticing, emerging on the other side of the universe. But if the universe has a true physical boundary, a place where space ends or transitions to something else, the experience could be very different. You might encounter a gradient in the density of matter, a region where galaxies become sparser and eventually disappear. You might find that the laws of physics change, that the constants of nature take different values, or that new forces or particles appear. You might reach a horizon beyond which you cannot pass, a boundary imposed by the expansion of space or by the structure of space-time itself. Or you might find that the concept of a boundary is meaningless, that the question of what lies beyond doesn't have an answer because there is no beyond, because the universe is all there is, and the very idea of an outside is incoherent. These are not just abstract speculations. They're questions that can be addressed, at least in principle, through observation and theoretical modeling. The challenge is that the scales involved are so vast and the distances so great that direct exploration is impossible. We can't send a spacecraft to the edge of the universe and see what's there. We're limited to observing the universe from our vantage point, here and now, and trying to infer the large-scale structure and extent from the patterns we see in the distribution of galaxies, in the cosmic microwave background, in gravitational waves, and in other cosmic messengers. But those patterns are subtle, and the inferences are uncertain. The universe is a complex system with many scales of structure and many processes at work. Separating the signal from the noise, distinguishing genuine features from artifacts of observation or analysis, is a formidable challenge. And yet, progress is being made. New surveys are mapping the distribution of galaxies with unprecedented precision, covering larger volumes of space and reaching to greater distances. New experiments are measuring the cosmic microwave background with greater sensitivity, detecting finer details and subtler correlations. New theoretical models are exploring a wider range of possibilities, from simple topologies to complex multiverse scenarios. One of the most exciting developments in recent years is the use of machine learning and artificial intelligence to analyze cosmological data. Machine learning algorithms can identify patterns and correlations that are too subtle or too complex for traditional statistical methods. They can search through vast parameter spaces, exploring different models and testing different hypotheses. And they can make predictions, generating simulated universes and comparing them to observations to see which models fit best. This approach is still in its early stages, but it's already yielding new insights and opening new avenues for exploration. Another promising direction is the development of new observational techniques, such as intensity mapping, which measures the aggregate emission from large numbers of galaxies rather than detecting individual sources. Intensity mapping can probe larger volumes of space and greater distances than traditional surveys, providing a more complete picture of the large-scale structure. It can also detect the faint glow of neutral hydrogen in the early universe, tracing the distribution of matter before the first galaxies formed. This could reveal subtle patterns or asymmetries that are hidden in other datasets, potentially providing evidence for cosmic boundaries or large-scale inhomogeneities. Yet, even as we develop new tools and techniques, we must remain mindful of the fundamental limitations of cosmology. We can only observe the universe from one location, at one moment in cosmic time. We can't travel to different regions of space and compare what we see. We can't rerun the universe to test different initial conditions. We're limited to a single realization of a cosmic experiment, and we have to make the most of it. This means being careful about our assumptions, questioning our models, and always looking for alternative explanations for the patterns we observe. It also means being humble about what we can know. The universe is under no obligation to be comprehensible to us, to fit our intuitions or our mathematical frameworks. It's possible that the true structure of reality is beyond our current capacity to understand, that there are aspects of the universe that we can never observe or explain. But that doesn't mean we should stop trying. The history of science is a history of pushing boundaries, of extending our reach and deepening our understanding, of finding ways to see further and think more clearly. The question of whether the universe has an edge is part of this larger project, this ongoing effort to map the contours of reality. It's a question that connects to fundamental issues in physics, mathematics, and philosophy. And it's a question that resonates with something deep in human experience: the desire to know where we are, what surrounds us, what lies beyond the horizon. For most of human history, the horizon was physical, a limit imposed by geography and technology. But as we've developed better tools and broader perspectives, the horizon has receded, and we've come to see that we live in a universe far larger and stranger than our ancestors ever imagined. Now we're pushing the horizon even further, exploring the possibility that the universe itself has limits, that there are boundaries or edges to the cosmos. This is not a retreat into a smaller, more confined worldview. It's an expansion of our understanding, a recognition that even infinity comes in different sizes and different forms, and that the structure of the universe might be more intricate and more surprising than we thought. A finite universe is not necessarily a smaller universe. It could be vast beyond comprehension, yet still have a definite size and shape. And a universe with boundaries might be more interesting, more structured, more revealing of the underlying laws of physics than a universe that simply goes on forever without variation or limit. The exploration of cosmic boundaries also touches on questions about the fate of the universe, about what will happen in the distant future as the expansion continues and the cosmos evolves. In a universe dominated by dark energy, the expansion will accelerate, and galaxies will move apart faster and faster. Eventually, the only galaxies we'll be able to see will be the ones in our local group, bound together by gravity. Everything else will have crossed the cosmological event horizon and disappeared from view. The universe will become a lonelier place, with vast, empty spaces separating the remaining islands of matter. But even within those islands, change will continue. Stars will exhaust their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. New stars will form from the remaining gas, but eventually the gas will run out and star formation will cease. The galaxies will grow dark, filled with the remnants of dead stars and the invisible presence of dark matter. Black holes will slowly evaporate through Hawking radiation, a quantum process that allows them to lose mass and energy over immense timescales. Eventually, even the black holes will disappear, leaving behind a universe that is cold, dark, and empty, filled only with the faint glow of radiation and the occasional particle created by quantum fluctuations. This future, sometimes called the heat death of the universe, is based on current models of dark energy and the long-term behavior of matter. But it's not certain. There are many unknowns, many aspects of physics that we don't yet understand. Dark energy might not be constant. It might evolve or decay, changing the expansion rate and the ultimate fate of the universe. There might be new processes, new forms of matter or energy that come into play at late times and alter the trajectory of cosmic evolution. And if the universe has boundaries or edges, the fate of different regions might be different, with some parts of the universe evolving in one way and others evolving differently. These considerations bring us back to the question of what it means for the universe to have an edge. If the universe is finite, then in some sense it's already bounded, limited in its total extent and total content. The expansion might be carrying the parts of the universe apart, but the universe as a whole remains a finite entity, a closed system with a definite amount of matter and energy. In such a universe, the laws of thermodynamics apply in a straightforward way, and the eventual heat death is a consequence of the universe evolving toward thermal equilibrium, a state where all energy is evenly distributed and no more work can be done. But if the universe is infinite, the situation is more complex. An infinite universe can have an infinite amount of matter and energy, and the concept of thermal equilibrium becomes less clear. Different regions of an infinite universe could be in different states, with some regions hot and others cold, some regions dense and others sparse. The universe as a whole might never reach a single equilibrium state because there's always more universe, more regions that are evolving independently. In this case, the fate of the universe depends not just on the laws of physics, but also on the initial conditions and the large-scale structure, on how matter and energy are distributed across the infinite expanse. The question of boundaries also relates to the problem of initial conditions, the question of why the universe started out the way it did. In the standard Big Bang model, the universe begins in a state of extremely high density and temperature, with matter and energy distributed almost uniformly. This initial state is highly special, highly ordered, and it requires an explanation. Why did the universe start out so uniform, so smooth? Why wasn't it chaotic, with large fluctuations and inhomogeneities? Inflation provides a partial answer to this question, explaining how a small region of space could have been stretched and smoothed to create the large-scale uniformity we observe. But inflation itself requires special initial conditions, a region of space filled with the inflaton field in the right state to drive the expansion. And this just pushes the question back. Why did such a region exist? Why did the inflaton field have the properties it did? Some models of eternal inflation suggest that inflation is a generic process, that it happens naturally in many regions of a larger multiverse, and that our universe is just one of many bubbles where inflation ended and matter formed. In this picture, the special initial conditions of our universe are not so special after all. They're just one realization out of many, selected by the fact that we happen to live here and observe from this vantage point. But this raises new questions, including questions about the boundaries of the multiverse. If there are many bubbles, many universes, how are they distributed? Is the multiverse finite or infinite? Do the bubbles interact, collide, merge? And if the multiverse has boundaries, what lies beyond them? These questions are even more speculative than the question of whether our universe has boundaries, because the multiverse, if it exists, is by definition beyond our direct observation. We can only infer its existence from theoretical considerations and from subtle signatures that might be imprinted on our universe as a result of interactions with other bubbles. One proposed signature is a pattern of circles in the cosmic microwave background, created by collisions between our bubble and neighboring bubbles during the inflationary era. Several groups have searched for such circles, and some have claimed to find hints of them, but the results are controversial and have not been confirmed. The cosmic microwave background is a noisy dataset, and it's easy to find patterns that look significant but are actually just random fluctuations. Distinguishing genuine signals from noise requires careful statistical analysis and independent confirmation, and so far the evidence for bubble collisions remains inconclusive. Another approach to probing the boundaries of the universe is to look for evidence of quantum fluctuations on very large scales. Quantum mechanics tells us that fields and particles are subject to uncertainty, that they fluctuate randomly at the smallest scales. During inflation, these quantum fluctuations were stretched to macroscopic sizes, creating the seeds of structure that eventually grew into galaxies and galaxy clusters. The pattern of these fluctuations depends on the details of the inflationary process, including the energy scale of inflation, the duration of inflation, and the shape of the inflaton potential. If inflation occurred in a finite region, or if the universe has a boundary, the pattern of quantum fluctuations might be different from what we'd expect in an infinite universe. There might be a cutoff at the largest scales, a suppression of fluctuations on scales larger than the size of the inflating region or the distance to the boundary. By measuring the power spectrum of the cosmic microwave background and comparing it to theoretical predictions, we can constrain the possible properties of the early universe, including the possibility of boundaries. Recent analyses of the Planck data have explored this possibility, looking for evidence of a finite universe or a boundary at large scales. Some studies have found hints of a suppression of power at the largest scales consistent with a finite universe, but the significance of this result is debated. The largest scales in the cosmic microwave background correspond to only a few independent measurements, because we only see one sky and can only divide it into so many regions. This means that the statistical uncertainty is large, and it's difficult to distinguish between genuine features and random fluctuations. To make progress on this question, we need more data, and in particular, we need data that probes larger scales or different aspects of the large scale structure. One way to do this is to study the distribution of galaxies at very large scales, using surveys that cover large fractions of the sky and reach to high redshifts. These surveys can measure the clustering of galaxies, the correlations between the positions of galaxies in different parts of the sky, and compare them to theoretical predictions. If the universe is finite, or if there are large-scale asymmetries or boundaries, they should show up as deviations from the expected pattern of clustering. Another approach is to study the polarization of the cosmic microwave background, the way the light is oriented as it travels through space. Polarization carries additional information about the early universe, including information about gravitational waves generated during inflation. Gravitational waves leave a distinctive pattern in the polarization called B-mode polarization, and detecting this pattern would provide strong evidence for inflation and constrain its properties. The search for B-mode polarization is one of the major goals of current and future cosmic microwave background experiments, and it could potentially reveal information about the boundaries or extent of the universe. Gravitational waves themselves offer another window on the large-scale structure of the universe. While the gravitational waves detected so far by LIGO and Virgo come from relatively nearby sources, future observatories could detect gravitational waves from the early universe, from events that occurred during or shortly after inflation. These primordial gravitational waves would carry information about the state of the universe at the earliest times, including information about the geometry and topology of space. If the universe is finite or has boundaries, the pattern of primordial gravitational waves might be different from what we'd expect in an infinite universe, and detecting this difference could provide evidence for cosmic boundaries. The study of neutrinos also offers potential insights into the large-scale structure of the universe. Neutrinos are nearly massless particles that interact very weakly with matter, allowing them to travel vast distances without being absorbed or scattered. In the early universe, neutrinos were in thermal equilibrium with the other particles. But as the universe expanded and cooled, they decoupled and began traveling freely. Today, there's a cosmic neutrino background analogous to the cosmic microwave background that fills the universe. This neutrino background has not yet been detected directly, but its existence is strongly supported by theoretical predictions and by indirect evidence from the cosmic microwave background and from the abundances of light elements produced in the Big Bang. The cosmic neutrino background carries information about the early universe that is complementary to the information in the cosmic microwave background. Because neutrinos interact so weakly, they decoupled earlier than photons, and they probe an earlier era. If the universe has large-scale structure or boundaries, the neutrino background might reveal patterns or asymmetries that are not visible in the photon background. Detecting the cosmic neutrino background is a formidable experimental challenge because the neutrinos have very low energies and interact extremely rarely. But several experiments are under development, and there's hope that in the coming years we'll be able to make the first direct detection of this relic radiation and use it to probe the large-scale structure of the universe. Another frontier in the search for cosmic boundaries involves the study of the very early universe, the moments just after the Big Bang, when the universe was in a state of extreme density and temperature. During this era, the physics is governed by processes that we can't study in laboratories, energies far higher than anything we can produce in particle accelerators. To understand what happened, we have to rely on theoretical models, extrapolating from known physics and making educated guesses about the behavior of matter and energy under extreme conditions. One of the key questions about the early universe is whether it underwent a period of inflation, and if so, what caused it and how it ended. Inflation is supported by many lines of evidence, including the flatness of space, the uniformity of the cosmic microwave background, and the spectrum of density fluctuations. But the details are uncertain, and there are many different models of inflation, each making slightly different predictions. By comparing these predictions to observations, we can narrow down the possibilities and potentially rule out some models. One of the predictions of many inflationary models is that the universe should have no large-scale asymmetries or preferred directions. Inflation is thought to have smoothed out any initial irregularities, leaving the universe homogeneous and isotropic on large scales. But if the observational anomalies in the cosmic microwave background are real, they suggest that the universe is not perfectly isotropic, that there's some preferred direction or axis. This could mean that inflation was not as complete as we thought, that there are remnants of pre-inflationary structure that survived the expansion. Or it could mean that something happened after inflation to create asymmetries, such as a collision with another bubble, or a transition to a different phase of vacuum. These possibilities are speculative, but they're testable, at least in principle. By studying the cosmic microwave background in greater detail, by mapping the distribution of galaxies more completely, and by developing better theoretical models, we can explore these scenarios and determine which, if any, are consistent with the data. The search for cosmic boundaries is not just a search for a physical edge or limit. It's a search for deeper understanding, for a more complete picture of how the universe is structured and how it came to be. One of the profound implications of the possibility of cosmic boundaries is that it challenges our assumptions about the nature of space and time. We're used to thinking of space as a container, a stage on which the drama of the universe unfolds. We think of time as a river flowing from past to future, carrying us along. But general relativity tells us that space and time are not fixed or absolute. They're dynamic, flexible, shaped by the presence of matter and energy. Space can expand or contract, curve or warp, and even split or join in complex ways. Time can flow at different rates in different places, and the distinction between space and time can become blurred near black holes or in the early universe. If the universe has boundaries, it means that space itself has limits, that there are places or directions where space comes to an end or transitions to something else. This is a strange and unsettling idea because it goes against our intuition that space is infinite and everywhere the same. But our intuitions are based on our experience in a small region of the universe, and they may not apply on cosmic scales. Just as the Earth seems flat when you're standing on it, but is actually curved when seen from space, the universe might seem infinite when observed locally, but turn out to be finite when viewed as a whole. The question of boundaries also connects to the nature of nothingness, of what it means for there to be nothing. In everyday language, nothing is the absence of something, the empty space between objects. But in physics, empty space is not nothing. It's a quantum field, seething with virtual particles that pop in and out of existence. Even the vacuum has energy, and that energy can have physical effects, such as the Casimir effect, where two metal plates in a vacuum are pushed together by the pressure of the quantum field. So when we ask what lies beyond the boundary of the universe, we're not asking about an empty void. We're asking about the nature of the quantum field, about whether there are regions where the field is different or where the usual laws of physics don't apply. Some theoretical models suggest that the boundary of the universe is not a sharp edge, but a gradual transition, a region where the properties of space change slowly from what we observe to something else. This transition region might be very large, spanning billions of light years, and the changes might be subtle enough that we wouldn't notice them unless we looked carefully. But the cumulative effect over large distances could be significant, creating observable patterns or asymmetries that could be detected with sensitive instruments. Other models suggest that the boundary is sharp, a discontinuity where the laws of physics change abruptly. This could happen at the edge of an inflationary bubble, where the inflatant field transitions from one value to another, or at the boundary between different phases of vacuum. In such a scenario, the boundary itself might be a source of interesting physics, with particles and radiation created at the transition, and possibly with observable effects that propagate into the interior of the universe. The question of what determines the location and properties of a cosmic boundary is deeply tied to the question of initial conditions and the nature of the laws of physics. If the universe is finite, why does it have the size and shape it does? If there are boundaries, why are they located where they are? These questions are analogous to the question of why the universe has the particular values of the fundamental constants that we observe, such as the strength of gravity or the mass of the electron. These constants seem arbitrary, not determined by any deeper principle, and they could have been different. But if they were different, the universe would be different, and in many cases it wouldn't support the formation of stars, planets, or life. This observation has led to the anthropic principle, the idea that the universe must have properties compatible with the existence of observers, because otherwise there would be no one to observe it. In the context of a multiverse, where different regions or bubbles have different values of the constants and different properties, The anthropic principle suggests that we should expect to find ourselves in a region where the conditions are right for life, regardless of whether such regions are common or rare. Similarly, if different regions have different sizes or different boundaries, we should expect to find ourselves in a region that's large enough and structured in such a way that observers can exist. This line of reasoning is controversial because it seems to replace explanation with selection, invoking the existence of observers as a fundamental principle rather than deriving the properties of the universe from deeper laws. But it also highlights the limitations of what we can learn from observation alone. If we're necessarily biased toward observing certain types of universes because those are the only ones that can support observers, then we can't directly test theories that predict a wide range of possibilities, because we'll always find ourselves in the subset that's compatible with our existence. Despite these philosophical challenges, the search for cosmic boundaries remains an empirical question, one that can be addressed through observation and measurement. We can map the distribution of galaxies, measure the cosmic microwave background, detect gravitational waves, and study other cosmic messengers. And we can use these observations to constrain the geometry, topology, and extent of the universe. We can test different models and see which ones are consistent with the data. And as our instruments improve and our data sets grow, we can push the boundaries of what's observable and potentially detect evidence for features that are currently beyond our reach. One of the most exciting prospects for future observations is the development of next-generation surveys and experiments that will probe the universe with unprecedented sensitivity and precision. Projects like the Vera Rubin Observatory, formerly known as LSST, will survey the entire visible sky repeatedly over many years, detecting billions of galaxies and mapping their positions and properties. This will allow us to study the large-scale structure of the universe in exquisite detail, measuring the clustering of galaxies, the distribution of dark matter, and the effects of dark energy on the expansion. Other projects, like the Euclid satellite and the Nancy Grace Roman Space Telescope, will focus on measuring the shapes and distances of galaxies, using weak gravitational lensing to map the distribution of dark matter, and using supernovae and other standard candles to trace the expansion history of the universe. These measurements will provide powerful constraints on the properties of dark energy and on the geometry of space, potentially revealing evidence for a finite universe or for large-scale asymmetries. On the cosmic microwave background front, experiments like the Simons Observatory and CMBS-4 are being developed to measure the polarization of the background radiation with much greater sensitivity than current experiments. These measurements will search for the B-mode polarization signal from primordial gravitational waves, and they'll also measure the small-scale structure of the background with higher precision, potentially revealing subtle features that could indicate a finite universe or a boundary. In the realm of gravitational waves, future detectors like LISA, the Laser Interferometer Space Antenna, will open a new window on the universe by detecting gravitational waves at much lower frequencies than LIGO and Virgo. LISA will be sensitive to waves from supermassive black hole mergers, from compact binaries in our galaxy, and potentially from cosmological sources such as phase transitions in the early universe. These detections could provide new information about the large-scale structure and history of the universe, complementing the information from electromagnetic observations. The study of neutrinos is also poised for major advances. Projects like the Deep Underground Neutrino Experiment, or DUNE, will study neutrinos in unprecedented detail, measuring their properties and interactions. While DUNE is primarily focused on particle physics, the techniques being developed could eventually be applied to the detection of the cosmic neutrino background, opening yet another window on the early universe. These diverse observational programs, spanning different wavelengths and different messengers, will provide a multifaceted view of the universe, allowing us to cross check results and build a more complete and robust picture. The question of cosmic boundaries is not something that will be answered by a single measurement or a single experiment. It will require the accumulation of evidence from many sources, the development of theoretical models that can explain the observations, and the careful analysis of data to separate genuine signals from noise and systematic errors. As we pursue this quest, we must also grapple with the limits of what's knowable. There are fundamental constraints on what we can observe, imposed by the speed of light, by the expansion of the universe, and by the quantum nature of fields and particles. We can never see beyond our cosmic horizon. The boundary set by the distance light can travel in the age of the universe. We can never observe regions that are receding from us faster than light, because light from those regions can never reach us, and we can never fully reconstruct the initial conditions of the universe, because information is lost in the process of expansion and evolution. These limitations are not failures of our instruments or our theories. They're fundamental features of the universe itself. They tell us that there are questions we might never be able to answer definitively, aspects of reality that might forever remain beyond our grasp. But they also tell us that the universe has structure, boundaries, horizons, and that these features are not just practical limitations, but are woven into the fabric of space-time itself. The recognition of these limits can be humbling, but it can also be liberating. It frees us from the illusion that we can know everything, that science will eventually answer every question and resolve every mystery. It reminds us that the universe is larger and stranger than our minds, that there will always be more to discover, more to explore, more to wonder about. And it focuses our attention on the questions we can answer, the observations we can make, the theories we can test, the boundaries we can actually approach. In that spirit, the search for cosmic boundaries is not just an abstract intellectual exercise. It's a concrete scientific program with specific observational targets, specific predictions to test, specific anomalies to investigate. It's a program that draws on the full range of modern cosmology, from the study of the cosmic microwave background to the mapping of large-scale structure, from theoretical models of inflation to the detection of gravitational waves. And it's a program that's making progress as new data comes in and new analysis techniques are developed. The anomalies in the cosmic microwave background, while controversial, have focused attention on the possibility that the universe might not be as uniform as we thought. The discovery of very large structures, like the Hercules Corona Borealis Great Wall, has challenged our assumptions about homogeneity on the largest scales. The hints of bulk flows and other asymmetries in the distribution of galaxies have raised questions about what lies beyond our observable horizon. None of these observations is conclusive on its own, but together they paint a picture of a universe that might be more complex, more structured, more bounded than the standard model suggests. At the same time, we must be cautious about overinterpreting the data. The history of cosmology is full of anomalies that turned out to be artifacts of observation or analysis, features that disappeared when the data was reanalyzed, or when better data became available. The cold spot in the cosmic microwave background, for example, has been the subject of intense scrutiny, with some researchers claiming it's a sign of exotic physics and others arguing it's just a statistical fluctuation. The truth might lie somewhere in between, or it might be something we haven't thought of yet. This uncertainty is part of what makes the search for cosmic boundaries so exciting. We're operating at the edge of our knowledge, pushing into territory where the data is sparse and the theories are speculative. We don't know what we'll find, and that's precisely why we're looking. We might discover that the universe is indeed finite, with a definite size and shape. We might find evidence for large-scale asymmetries or gradients that point toward a boundary beyond our horizon. We might detect signatures of a multiverse, collisions with other bubbles, or transitions between different phases of vacuum. Or we might find that the universe is infinite after all, that the anomalies are just noise, and that the standard model is correct as far as we can see. Whatever we find, the search itself will advance our understanding. It will push the development of new observational techniques, new theoretical models, new ways of analyzing data. It will force us to think carefully about what we mean by concepts like space, time, infinity, and boundary. It will connect cosmology to other areas of physics, from quantum mechanics to thermodynamics, from particle physics to general relativity. And it will remind us that the universe is not just a collection of objects, but a coherent whole, a system with structure and properties that can be studied and understood. One of the deep connections that emerges from this investigation is the relationship between the very large and the very small. The structure of the universe on the largest scales is determined by processes that occurred on the smallest scales in the earliest moments. The quantum fluctuations that were stretched by inflation to create the seeds of galaxies were once smaller than an atom, smaller than a nucleus, perhaps smaller than anything we can imagine. The laws of physics that govern the behavior of matter and energy on cosmic scales are the same laws that govern the behavior of particles and fields in accelerators. The boundaries of the universe, if they exist, might be intimately connected to the boundaries of quantum mechanics, to the limits of what's knowable or measurable at the smallest scales. This connection between the very large and the very small is one of the central themes of modern physics, and it's a theme that runs through the search for cosmic boundaries. The question of whether the universe is finite or infinite is related to the question of whether space and time are continuous or discrete, whether they're made of something more fundamental or whether they're emergent from a deeper structure. The question of what lies beyond the cosmic horizon is related to the question of what happens inside a black hole, beyond the event horizon where classical physics breaks down and quantum effects become important. These questions are difficult, perhaps even unanswerable with current tools, but they're not beyond the reach of scientific inquiry. We can make progress by exploring the connections, by testing predictions, by developing new theories and new experiments. We can look for signatures in the cosmic microwave background that might reveal the quantum structure of spacetime. We can study black holes and their evaporation through Hawking radiation, looking for clues about what happens at the boundaries of spacetime. We can develop quantum theories of gravity that might predict the existence and properties of cosmic boundaries. The search for cosmic boundaries is thus part of a larger project, the quest to understand the fundamental nature of reality. It's a project that spans scales from the smallest particles to the largest structures, that connects the beginning of time to the end of time, that brings together observation and theory, experiment and mathematics. It's a project that requires patience, creativity, rigor, and imagination. And it's a project that speaks to something deep in human nature, the desire to explore, to understand, to push beyond the known into the unknown. As we stand here now in the early decades of the 21st century, we're in a unique position in the history of this project. We have instruments that can see to the edge of the observable universe, that can detect the faint whispers of the Big Bang, that can measure the properties of space and time with exquisite precision. We have theories that can describe the evolution of the universe from the first fraction of a second to the present day, that can predict the formation of structure and the behavior of matter and energy. And we have questions, deep and profound questions, about the extent and nature of the cosmos. Questions that our ancestors could barely imagine, but that we can now begin to address. The possibility that the universe has an edge is one of those questions, and it's a question that we're getting closer to answering. Not because we've found definitive evidence for a boundary, but because we're developing the tools and the understanding needed to search for such evidence, to test the predictions of different models, to explore the implications of different scenarios. We're mapping the universe in unprecedented detail, measuring its properties with unprecedented precision, and thinking about its structure with unprecedented sophistication. The journey toward understanding cosmic boundaries is not a straightforward one. It involves dead ends, false starts, controversies, and debates. It requires us to question our assumptions, to challenge our intuitions, to be willing to consider possibilities that seem strange or counterintuitive. It requires collaboration across disciplines, between observers and theorists, between cosmologists and particle physicists, between mathematicians and philosophers. And it requires a willingness to live with uncertainty, to embrace the fact that we don't have all the answers and might never have them. But this uncertainty is not a weakness, it's a strength. It's what drives us forward, what motivates us to build better instruments, to develop better theories, to ask better questions. It's what makes science not just a body of knowledge, but a process, a method, a way of engaging with the world. And it's what makes the search for cosmic boundaries not just a technical exercise, but a profound human endeavor, an attempt to understand our place in the universe and the nature of the reality we inhabit. As we look to the future, we can anticipate that the next few decades will bring major advances in our understanding of the large-scale structure and extent of the universe. New surveys will map billions of galaxies, tracing the cosmic web in 3 dimensions and revealing patterns that are currently hidden. New experiments will measure the cosmic microwave background with unprecedented sensitivity, detecting features that are currently below the noise threshold. New theories will explore a wider range of possibilities, from simple, finite universes to complex multiverse scenarios, and will make predictions that can be tested against observations. We can also anticipate that the search for cosmic boundaries will continue to raise deep questions about the nature of space, time, and reality. Questions about infinity and finitude, about what it means for something to exist beyond our observation, about the relationship between the part and the whole. These questions have been pondered by philosophers and theologians for millennia. But now they're becoming empirical questions, questions that can be addressed through observation and experiment. This transformation of ancient philosophical puzzles into modern scientific problems is one of the great achievements of cosmology, and it's a transformation that continues to this day. The question of whether the universe has an edge is, in many ways, a question about limits. Not just the limits of the universe, but the limits of knowledge, the limits of observation, the limits of human understanding. It's a question that forces us to confront what we can and cannot know, to distinguish between what's fundamentally unknowable and what's merely unknown at present. And it's a question that reminds us that the universe is not required to be simple or comprehensible, that it might have features and properties that challenge our deepest assumptions about reality. Yet, despite these challenges, or perhaps because of them, the search for cosmic boundaries continues. It continues because we are curious, because we want to know, because the questions are too important to ignore. It continues because we have the tools to make progress, the instruments to gather data, the theories to interpret observations. It continues because every answer leads to new questions. Every discovery opens new avenues of inquiry. Every boundary we approach reveals new horizons beyond. The universe stretches out around us, vast and complex, filled with structure on every scale, from the smallest particles to the largest superclusters. We are embedded in this structure, part of it, shaped by it, and yet somehow able to step back and observe it, to measure it, to understand it. This ability to comprehend the cosmos, to trace its history and predict its future, to ask questions about its ultimate extent and nature, is one of the most remarkable features of human existence. We are, as far as we know, the only part of the universe that is capable of understanding the universe, the only observers who can look out at the stars and ask where they end, whether there are boundaries, what lies beyond. This capacity for wonder and inquiry is what drives the search for cosmic boundaries. It's what motivates astronomers to spend long nights at telescopes gathering photons from distant galaxies. It's what drives theorists to develop complex mathematical models, exploring the implications of different geometries and topologies. It's what inspires experimentalists to build ever more sensitive instruments, pushing the boundaries of what's detectable. And it's what brings together the entire cosmological community, from graduate students to senior scientists, from observers to theorists, all working toward a common goal: to understand the universe in its totality, including its extent, its boundaries, its ultimate nature. The search is far from over. We have hints, clues, suggestive patterns in the data, but we don't yet have definitive answers. We have theories, models, scenarios, but we don't yet know which, if any, are correct. We have instruments, surveys, experiments, but we need more data, more observations, more measurements. The road ahead is long, and there will be many twists and turns, many surprises and setbacks. But the direction is clear. We are moving toward a deeper understanding of the universe, toward a more complete picture of its structure and extent, toward answers to some of the most profound questions we can ask. Whether the universe turns out to be finite or infinite, bounded or unbounded, the journey toward understanding it will have been worthwhile. We will have pushed the boundaries of knowledge, expanded our understanding of reality, and deepened our appreciation for the cosmos we inhabit. We will have developed new tools, new techniques, new ways of thinking that will find applications beyond cosmology in other areas of science and beyond. And we will have satisfied, at least partially, that deep human need to know, to understand, to make sense of the world around us. The question of cosmic boundaries is thus not just a question about the universe. It's a question about ourselves, about our place in the cosmos, about our capacity to understand and our willingness to explore. It's a question that connects us to our ancestors, who looked up at the same stars and wondered about the extent of the heavens, and to our descendants, who will inherit our discoveries and continue the search. It's a question that reminds us that we are part of something much larger than ourselves, part of a universe that stretches beyond our sight and our imagination, yet which we can still study and comprehend through the power of observation, reason, and mathematics. As we continue this search, mapping the cosmos and probing its boundaries, we do so with a sense of humility and wonder. Humility because we recognize how much we don't know, how vast the universe is compared to our small corner of it, how limited our observations are compared to the totality of what exists. Wonder because despite these limitations, we can still see so much, understand so much, reach so far. We can see galaxies billions of light years away, trace the history of the universe back to its first moments, predict its future evolution over trillions of years. We can measure the curvature of space, detect the ripples of gravitational waves, probe the quantum fluctuations that seeded all structure. These achievements are not just technical accomplishments, they're triumphs of the human spirit, demonstrations of what we can achieve when we work together toward a common goal. The search for cosmic boundaries is a collective endeavor involving thousands of scientists across dozens of countries, using facilities and instruments that represent the culmination of decades of development and refinement. It's a search that transcends national boundaries, political differences, cultural divides, bringing together people from all backgrounds in pursuit of a shared understanding. And it's a search that will continue, generation after generation, as long as there are people who look up at the night sky and wonder. Wonder about the stars and galaxies, about the structure and extent of the cosmos, about our place in it all. Wonder about whether the universe goes on forever, or whether it has an edge somewhere out there beyond our sight, but within our reach to imagine and perhaps to detect. Wonder about what we'll find when we push our observations further, when we develop better theories, when we ask better questions. The universe might have an edge, a boundary, a limit to its extent, or it might go on forever, infinite in size and scope. We don't yet know which is true, but we're getting closer to finding out. Closer through better observations, closer through deeper theories, closer through more sophisticated analysis, closer because we're asking the right questions and developing the tools to answer them. Closer because we're willing to challenge our assumptions, to consider possibilities that seem strange or counterintuitive, to follow the data wherever it leads. This is where we are now, at a moment of transition in our understanding of the cosmos. The standard model of cosmology has been remarkably successful, explaining a vast range of observations with a relatively simple set of assumptions. But cracks are appearing, anomalies that don't quite fit, hints that the universe might be more complex than we thought. Whether these cracks will grow into fractures that require a fundamental rethinking of cosmology, or whether they'll turn out to be minor issues that can be resolved within the existing framework, remains to be seen. But either way, the process of investigating them, of testing them, of exploring their implications is advancing our understanding. The possibility of cosmic boundaries is one of these cracks, one of these hints that something interesting might be happening at the largest scales. It's not yet a proven fact, not yet a confirmed discovery, but it's a live possibility, a hypothesis that's being actively investigated by researchers around the world. And as we investigate it, we're learning more about the universe, more about the nature of space and time, more about the laws of physics that govern the cosmos. We're developing new techniques for analyzing data, new methods for modeling complex systems, new ways of thinking about structure and extent. This learning, this process of discovery, is valuable regardless of what we ultimately find about cosmic boundaries. If we discover that the universe is finite, it will be one of the great revelations in the history of science, transforming our understanding of reality and our place in it. If we discover that the universe is infinite after all, that the anomalies are just artifacts or statistical flukes, it will still have been worthwhile because we'll have developed a deeper understanding of the universe and more confidence in the standard model. And if the answer remains uncertain, if the data continues to be ambiguous and the theories inconclusive, we'll still have advanced our knowledge, pushed our observations further, refined our understanding of what's possible. This is the nature of science, of exploration, of the quest to understand. It's not about reaching a final destination or obtaining complete knowledge. It's about the journey, about the process of asking questions and seeking answers, about the gradual accumulation of knowledge and the continual refinement of understanding. It's about being willing to embrace uncertainty, to live with ambiguity, to recognize that some questions might take generations to answer and some might never be answered at all. But it's also about hope, about the belief that we can make progress, that we can learn more, that we can push back the boundaries of ignorance and expand the realm of knowledge. The search for cosmic boundaries embodies this hope, this belief that even the deepest questions about the nature of reality can be addressed through careful observation, rigorous analysis, and creative thinking. It's a search that requires patience and persistence, but also imagination and courage. Patience to wait for better data, persistence to continue when results are inconclusive, imagination to conceive of new possibilities, courage to challenge established ideas. As this search continues, it will undoubtedly produce surprises, discoveries that we don't anticipate, insights that come from unexpected directions. The history of cosmology is full of such surprises. From the discovery of the expanding universe to the detection of the cosmic microwave background, from the realization that most of the universe is made of dark matter and dark energy, to the discovery of gravitational waves. Each of these discoveries transformed our understanding of the cosmos and opened new avenues of inquiry. The search for cosmic boundaries has the potential to produce similar transformations, to reveal new features of the universe that we haven't yet imagined. And even if the ultimate answer to the question of cosmic boundaries remains elusive, the search itself will have value. It will drive technological innovation as we develop better telescopes, better detectors, better analysis tools. It will inspire young people to pursue careers in science, showing them that there are still great mysteries to solve, still frontiers to explore. It will foster international collaboration, bringing together researchers from different countries and cultures to work toward a common goal. And it will enrich our collective understanding of the universe, adding depth and nuance to the picture of reality that we're collectively constructing. This picture is far from complete. There are vast gaps in our knowledge, fundamental questions that remain unanswered, mysteries that defy explanation. But the picture is also remarkably detailed and coherent, a testament to centuries of observation, experiment, and theoretical work. We know the age of the universe to within a fraction of a percent. We can trace its history from the first microsecond to the present day. We can predict the formation of structure and the evolution of galaxies with remarkable accuracy. And we're now in a position to ask questions about the ultimate extent and boundaries of the cosmos, questions that our predecessors could barely formulate. This progress is not guaranteed to continue. Science is a human endeavor, and it depends on continued investment, continued support, continued commitment to the values of curiosity, rigor, and openness. It depends on societies that value knowledge and understanding, that support education and research, that recognize the importance of asking questions even when the answers are not immediately practical or useful. And it depends on individuals who are willing to dedicate their lives to the pursuit of understanding, to spend years analyzing data, developing theories, conducting experiments, all in service of answering fundamental questions about the nature of reality. The search for cosmic boundaries is one expression of this commitment, this dedication to understanding. It's a search that will occupy cosmologists for years to come as they collect more data, refine their models, test new hypotheses. It's a search that will evolve as technology advances, as new instruments come online, as new analysis techniques are developed. And it's a search that will continue to captivate public imagination. Because the question of whether the universe has an edge speaks to something deep in human consciousness, a desire to know the limits of our world, to understand the boundaries of existence. We are, all of us, inhabitants of this universe, living within whatever boundaries it might have, subject to whatever laws govern its behavior. We did not choose to be here, did not design the universe or set its parameters. But we find ourselves here nonetheless, conscious beings in a vast and complex cosmos, capable of observing and understanding it. This capacity is precious, perhaps rare, and it brings with it a responsibility to use it well, to seek understanding, to push the boundaries of knowledge as far as we can. The universe might have an edge, and we might be getting close to it. Not close in the sense of approaching a physical boundary, but close in the sense of having the tools and the understanding needed to detect evidence for such a boundary, to test the hypothesis, to determine whether it's true. This is a remarkable moment in the history of cosmology, a time when questions that were once purely philosophical are becoming empirical, testable, addressable through observation and measurement. As we stand at this moment, looking out at the cosmos and contemplating its extent, we do so with a mixture of confidence and humility. Confidence because we've come so far, learned so much, developed such powerful tools for probing the universe. Humility because we know how much remains unknown, how vast the universe is compared to our observations, how limited our understanding is compared to the full complexity of reality. But this combination of confidence and humility is healthy, productive, conducive to good science. It keeps us honest, prevents us from overreaching or claiming to know more than we do, while also inspiring us to continue the search, to push further, to ask deeper questions. The question of cosmic boundaries is one of those deeper questions, a question that pushes us to the limits of what we can observe and understand. It's a question without a simple answer, without an obvious resolution. But it's a question worth asking, worth pursuing, worth dedicating resources and effort to address. Because in asking it, in pursuing it, we learn more about the universe and about ourselves. We develop new tools, new techniques, new ways of thinking. We train a new generation of scientists equipped to tackle even harder problems. And we add to the store of human knowledge, expanding our collective understanding of the cosmos. This understanding is not complete, and it never will be. There will always be more to learn, more to discover, more questions to ask. The universe is too vast, too complex, too subtle to be fully comprehended by any finite intelligence. But we can make progress. We can learn more. We can expand our understanding bit by bit, generation by generation. And as we do, we're not just accumulating facts or data. We're constructing a narrative, a story about the universe and our place in it, a story that gives meaning and context to our existence. The question of whether the universe has an edge is part of this story, a chapter that's still being written. We don't yet know how the chapter will end, what the final answer will be, but we're actively writing it through observation and theory, through experiment and analysis. And as we write it, we're also reading it, learning from it, being shaped by it. The universe is not just something we observe, it's something we're part of, something that made us and continues to influence us. Understanding it is a way of understanding ourselves, of coming to terms with our origins and our fate, of finding our place in the vast cosmic landscape. So we continue the search, mapping the cosmos, probing its boundaries, asking questions about its extent and nature. We do so knowing that the answers might be surprising, might challenge our assumptions, might force us to rethink fundamental aspects of our cosmological worldview. But we do so also knowing that the search itself is valuable, that the process of inquiry is as important as the destination, that the journey toward understanding is what makes us human. The universe might have an edge, and we're getting close to it, close to the point where we can answer this ancient question with modern data and sophisticated theory. Whether we find a boundary or confirm infinity, whether we discover new structure or validate existing models, the search will have been worthwhile. It will have expanded our knowledge, deepened our understanding, and reminded us of the profound beauty and mystery of the cosmos we inhabit. A cosmos that stretches beyond our sight, beyond our imagination, yet which we can still explore through the power of observation, reason, and relentless curiosity about what lies at the furthest reaches of existence.